Okay, I'm going to be working on section 6.6, which is improper integrals, and I'm going to be working through the odd problems, starting with number 5, and then I'll work through probably through 31. Uh-oh. Okay. Get a little bit of water in here. All right, so the first problem that we'll do, number 5, is integral from 3 to infinity of 1 over x minus 2 raised to the 3 halves dx. All right, so what we have here, remember there's 2 types of improper integrals that we're looking at. Type 1 were called infinite intervals, and that would be where our interval is actually infinite. And then the other type that we have in this section, the type 2, is a discontinuous integrand, which would mean that we have some discontinuity inside the integrand here, somewhere where maybe the denominator goes to 0 when the numerator goes to a fixed number. So with those two types of integrals in mind, let me first just take a look at the number line and realize I'm integrating from 3 to infinity. So if here's 0, here's 3. I'm looking out this direction forever, and I'm trying to find kind of like the area underneath this curve. Now, I don't really know what the curve does. Let's see, at 3, if I plug 3 in here, I get 3 minus 2 is 1. 1 to any power is 1. 1 over 1 is still 1. So I know I'm up here. And then as x gets bigger, as this gets larger, this ratio gets smaller. So I know that this does drop down like this. And I'm trying to find the area underneath here forever, to the right. Now, what I also need to consider here is whether or not my discontinuity is in my interval. So we can see that if we let x be 2, we get 0 here, and we're going to have a discontinuity. But 2 is not in my interval. 2 is here, so I'm not even going to consider that. So the approach here now, that I have an idea of what it looks like, is to rewrite this using the definition. This is going to be equal to the limit as t goes to infinity of the integral from 3 to t, and then the integrand, 1 over x minus 2 to the 3 halves dx. So all we do with these type 1 integrals is replace the infinity symbol with t, and then we do a limit. So we work this out as if t is a fixed number, and then at the end of the problem we'll let t go to infinity. So this antiderivative here we need to determine, and that can be done with a simple basic substitution. So I'll show a substitution on this problem in the future. I may not do this. We'll just see how things go here. If I take this integral and let's turn it into an indefinite integral. This is what we spent a couple of weeks on. If we're trying to find the antiderivative here, we can just let u be equal to x minus 2. Du can be just dx. And then I can rewrite the integral as 1 over u to the 3 halves du. And that's just the same as integral u to the negative 3 halves du. Let me shut this door real quick. All right, now we're going to actually just use the power rule. So I'm going to add 1 to this. If you add 1 to that, you get negative 1/2. So this will be equal to 1 over negative 1/2 u to the negative 1/2 plus a constant. But whenever we're doing definite integrals, we don't need to consider the constant of integration because it's always going to cancel out. I'll probably show you that in class. So this is going to be equal to, well, we flip and reciprocate there. So it's negative 2 u to negative 1/2. And then u was x minus 2. So negative 2 x minus 2 to the negative 1/2. All right, that's my antiderivative. So I'm going to come back over here now, and I'm going to write limit t goes to infinity. And then I have, let me put in parentheses here, negative 2 times x minus 2 to the negative 1/2. And then I'm going to evaluate that, because I've actually taken the antiderivative, I'm going to evaluate that at 3 in t. All right, so this is what we talked about in class. This is the fundamental theorem of calculus. You find the antiderivative, then you evaluate at the two endpoints. You subtract. So now I have, I'm going to keep my limit, keep writing my limit as I go here until I actually take the limit. I have limit t goes to infinity of, all right, in here we're going to have two things. All right, we're going to have what we get when we plug t in, then we're going to have what we get when we plug 3 in. So since I'm always going to have that format, I'm going to do 2 sets of parentheses, and then I'll close off the parentheses for the limit. So I'm going to plug t into here. If I do replace the x with t, it's just going to be t. Also, while I'm doing this, I'm going to rewrite this. This is going to be -2 over x minus 2 to the positive 1/2, because I'm dropping it down, but positive 1/2 means square root. Oh, forgot to replace the x with t. And then I'm going to do the same thing, -2 over the square root of, now I plug 3 in here, 3 minus 2. All right, so now I just need to figure out what this is. So if I let t go to infinity, if t goes to infinity, I know that this becomes infinite. Square root of infinity is still infinity, and then I have a fixed number over infinity, which is going to go to 0. So we have, on top it's -2, the bottom is headed towards infinity. That ratio will get smaller and smaller, which means that this one will go to 0. Minus, now over here, 3 minus 2 is 1, square root of 1 is 1, -2 over 1 is -2, so I'm going to subtract -2, and so the result is positive 2. So the area underneath that curve from 3 over to infinity forever, that area is converging to 2. And that's it for that one. So now let's take a look at number 7. Integral -infinity to 0 of 1 over 3 minus 4x dx. All right, so again, I'm going to take a look at the interval here. Here's 0. We're going out this direction to infinity, and whatever the function's doing, I'm trying to find the area underneath that curve to the left of 0. So what I also need to figure out is, do I have a discontinuity in this interval? So I take a look at the denominator and I ask myself, when is that 0? Make sure it's not in this interval. So if I take this and I solve this for x, I get 3/4, positive 3/4, which is over here. So my discontinuity is not in my interval. So I don't need to consider it at all. All right, so next thing to do would be to actually determine the antiderivative of this. I'm not going to go through the work, but if you made a substitution, u is equal to 3 minus 4x, du would be -4 dx, and then you could scale, -1/4 du is dx, and then you go through and you rewrite this, and what you would get is this. So I'm going to actually write this down, rewrite this as limit as t goes to -infinity of integral t to 0 of 1 over 3 minus 4x dx. And then using that substitution, I find the antiderivative of this. So again, I'm not going to show that. But this will be equal to the limit as t goes to -infinity of, now here's my antiderivative. It's -1/4 natural log of 3 minus 4x. And then evaluated t to 0 like that. Then I know that to evaluate this, I need to split this up into two pieces, plug in 0, plug in t. So I'll do that up here. So this will be equal to limit t goes to negative infinity of, let's see, two things here. So first we plug 0 in. So 4 times 0 is 0, 3 minus 0 is 3. So I just get negative 1/4 natural log of 3. Then I plug in t. So t goes in here. I just rewrite the whole thing. Negative 1/4 natural log of 3 minus 4t. All right, that's this t in here. And then at the end, I let t go to infinity, or negative infinity. So we have to pay attention to the signs here, make sure all this works out. So nothing happens here. So I have negative 1/4 natural log 3. And then here, if I let t go to negative infinity, I have a negative 4 times negative infinity. Really, you can't really do that, but a negative times a negative is positive. So I get 3 plus a number, and that number is becoming infinite. So really I'm saying what's natural log of an infinitely large number? We take a look at the natural log function, which looks like this, and we ask ourselves what happens as we go to infinity. So as we go out here, the function actually continues to rise slowly, but it does go to infinity. So I know that this entire thing goes to infinity, and it doesn't matter, I'm multiplying it by negative 1/4 and then subtracting it. The idea is that this whole thing becomes infinite. So I've got something like this, an infinite number. So the area under the curve is this constant plus an infinitely large number, which means that it doesn't go to a specific number. So we say that this diverges. And we're done. Hey, what's up? Good. They're using that other conference room for something else. What are you working on? Okay. Yeah? Yeah.
And it's the algebra that's screwing me up. It's mainly the system of equations.
Okay. Are you working on the homework problem for the online class or the?
Well, I was stuck on one of them, but
Okay.
I'm doing both.
Okay. Well, do you have a question? Because we can go over something.
Yeah.
Okay. Forgot your book?
No, I don't have mine on the laptop. I think I can look it up on my phone.
Yeah. All right, you look it up. I'm going to work through this one real quick.
Okay.
Okay, so in this one, we're integrating from 2 to infinity, so this way. And then e to the negative 5p, that doesn't ever have a discontinuity, so I don't need to worry about it. So I just need to find the antiderivative here. So let me first change this over. Limit t goes to infinity of the integral 2 to t. And then now e to the negative 5p dp, which equals the limit as t goes to infinity. And now let's get my antiderivative. So the antiderivative of e to the negative 5p is negative 1/5 e to the negative 5p. I'm evaluating that from 2 to t. Now, to do this integration from here to here, I actually looked at this and did a basic substitution. U is equal to negative 5p, and then du is negative 5 dp, and then I scale negative 1/5 du is dp, and then I rewrote the integral, and then it got me this. So I'm not showing that. And now all I have to do is plug in the two ends or two endpoints of the interval, which are t and 2, and subtract those two. So I'll do that up here, remembering that I have a limit sitting out in front of everything. Limit t goes to infinity of, I'm going to have two things being subtracted. So first I plug t in for p, so I get negative 1/5 e to the negative 5t, and then I plug in 2, I get negative 1/5, e to the negative, let's see, 2 times 5, so negative 10. All right, now this is a little bit tricky, so you got to be a little careful with this. You need to figure out what happens when t goes to positive infinity right here. So if I take a positive number and multiply it times negative 5, this is a negative number. So we're really asking ourselves, what happens if you take e and raise it to a number that's really, really big but negative? And there's two ways to look at this. One way would be you look at the e function, the exponential function, looks like this. And when you say take e and raise it to a very, very large negative number, that means you go out here, way out here on the x-axis and pick a very, very large negative number and then do e of that, and it's going to be a very, very small positive number because this is approaching 0. So we can say that this heads to 0. That's one approach. The other approach is to rewrite this right here as 1 over e to the positive 5t, so negative exponents drop down. And then when you let t go to infinity, this really turns into 1 over e to the positive infinity. And now you're looking, what does e do if you go out to positive infinity? So if you go this way, e gets very large, and so you have 1 divided by a really, really big number. That ratio gets smaller, so you get 0 here. So either way you do it, you're going to get 0. So this right here, when you take the limit, it goes to 0. And then this over here, nothing happens to it when t goes to infinity. So what you're left with is just this piece. So the negative and or minus the negative becomes plus, so you get 1/5 e to the negative 10. You could leave it like that, or you could put 1 over 5e to the positive 10. And e to the 10th power is some number, and then times 5, and then divide that into 1, and that's a number. So this interval converges to that value. Did you find it? Okay. All right, integral. It's number 9. 0 to infinity. Just let me know when you get it, okay? All right, on this interval, or this integral, we're looking from 0 to positive infinity, so we're looking that way. The only place we have a discontinuity is when this is 0, and that's going to happen if x is negative 1. If x is negative 1, that becomes 0. But negative 1 is over here, so I don't need to consider that. All right, so before I begin this, I'm actually going to take a look at this integrand. Make sure I can integrate this before I proceed. So I'm going to set up an indefinite integral real quick and try and figure out how to integrate this. And after looking at it for a few seconds, minutes, hours, I don't know, it'll depend on you, you'll realize it's just a basic substitution. And we have the derivative x squared dx. We've got the derivative of this up on top, so we can rewrite this integral as integral, let's see, this part right here is going to be part of our du, and it's 1 over the square root of u, so 1 over root u. And then this x squared dx becomes the 1/3 du, so 1/3 comes out du. And this is really just 1/3 integral u to the negative 1/2 du. And then we integrate 1/3 times, we add 1 to this, we get 1/2. 1 over 1/2 is 2. U to the positive 1/2 plus a constant. And that's just 2/3 u, but u was 1 plus x cubed to the 1/2, which is the same as the square root. So I'm going to come back over here. I'm going to rewrite this as limit t goes to infinity of the integral from 0 to t of x squared over square root 1 plus x cubed dx. Now find the antiderivative, which we did already. So limit t goes to infinity of this antiderivative, which is this, 2/3 square root 1 plus x cubed, and we're evaluating 0 to infinity. And you can see what's going to happen here. Limit t goes to infinity, or sorry, yeah, infinity of, we have two things being subtracted here. So if I go to infinity here, this becomes infinite. Square root of infinity is still infinity times 2/3. So this is becoming infinite. And then over here, if we plug in 0, we just get what, like a 1 in here, and then we get 2/3. So this is becoming infinite, and that's just going to the number 2/3. So this whole thing blows up, becomes infinite, which means that this integral diverges.
I guess.
You got it. You want to work through the whole thing, or you have a specific question, like at a certain point? What do you prefer?
This one, I get stuck.
You get that email about the bonus?
Yeah.
Okay.
But I think it's already over.
That's what?
It was already.
All right, number 13. All right, so in this problem, we are integrating from negative infinity to positive infinity, so over the entire real number line. Fortunately, this function does not have any discontinuities. I could rewrite that as this, and the denominator is never 0. So we're good to go. We can just integrate. But the way we do this is we actually break it up. So if we're going to go over the entire number line, all the way out this direction, all the way out this direction, everything in between, what we'll do is split it into two integrals, and I can split it anywhere I want. I could split it at 2, at 5, at -10, but the most natural place to split it would be at 0. So we're going to basically find the area on this side and this side, add the two areas together. So this integral becomes integral from negative infinity to 0 of x e to the negative x squared dx, plus the integral from 0 to infinity of x e to the negative x squared dx. All right. Now, I'm going to need the antiderivative of that, so I'm going to work on that right here. This is a basic u sub. U is negative x squared. Did he knock? I saw him. I didn't hear any knocking. Derivative of this is negative 2x dx. We have an x dx off by -2, so scale that out. And so this becomes integral -1/2 e to the u du. So replace that with u. X dx gets replaced with -1/2 du. And the antiderivative of this, of course, is itself plus a constant, which is equal to -1/2 e to the negative x squared. So that's the antiderivative. And so now I'm going to come back over here. I'm actually going to have to set up two separate limits. So maybe I'll put this up here. We're going to have this first one, which will be the limit as t goes to negative infinity of the, we're going to go ahead and do the antiderivative. Antiderivative of this, which is this, -1/2 e to the negative x squared, evaluated from negative infinity, which is my t, up to 0, and then plus another limit as t goes to positive infinity this time of the antiderivative of this, which is still this, evaluated this time from 0 to infinity, but infinity is my t. So that's it right there. Now, each one of these requires that I plug in 0, then t, and subtract, and then plug in t, and plug in 0, and subtract, and then take my limits. Notice the limits are going two different places, though. Negative infinity here, positive infinity here. So let's see if that changes anything or how that affects things. Limit t goes to negative infinity. And then I'm going to have two things in there. So first let's plug in 0. 0 squared 0, negative 0 is still 0, e to the 0 is 1. Negative 1/2 times 1 is negative 1/2. And then when we plug in t, let me give myself a little more room here. Plug in t, get negative 1/2 e to the negative t squared. Then we have plus, limit t goes to positive infinity this time, of two things subtracted here. So we plug in t first, get negative 1/2 e to the negative t squared. And then we plug in 0, we get the same thing we got over there, negative 1/2. All right, let's plug in negative infinity, and we're going to plug it in for t here. So if I take a negative number and square it, it's positive. So a very large negative number squared, it's going to be a very large positive number. So this right here is headed towards positive infinity, but then there's a negative in front of it, so that makes it negative infinity. So we have e raised to the negative infinity, which I just showed you in a previous problem, that goes to 0. So this thing goes to 0, and that thing doesn't matter. The whole thing goes to 0. So all I have is negative 1/2 here. Plus, now over here, same sort of thing. I'm plugging in infinity in for t, and I'm squaring it, so I'm going to get positive infinity. Then I'm subtracting it, so I get negative infinity, and then e raised to that, and that goes to 0. And then the whole thing goes to 0. And then over here we get minus is plus, so you get plus 1/2, which is equal to, if you add these two together, you get 0. So we get 0 as our total area for that one. Kind of interesting. I wonder if it has, if I have time to show the graph of that one up here. What number was that? 13. Okay.
When you have the integrals before you split them up, you distribute to the negative. So it would be like negative x over such and such and plus 1 over.
Where are you looking? Yeah, if you're going to distribute the negative, but where did the negative come from?
From negative 1. Because they're both negative.
They're both negative. Then put a plus there. Put a plus. Make that a plus, and then put a negative on that one. And then you could pull a negative out of both if you want.
Okay.
And then make it a minus.
All right, thank you.
What was it? I don't know if I have time to graph this. But I won't. But essentially what's happening is that the area, part of the graph is above the x-axis, part of it's below, and those areas together wipe each other out, and you get a net area of 0. All right, let's take a look at 15. Okay, for 15, we have integral negative infinity to 0 of z e to the 2z dz. All right, so I'm going to start by just making sure I don't have any issues. I'm looking from 0 to the left. This function doesn't have any discontinuities, so it should be okay to integrate without any issues. But I need the antiderivative of that, and that's going to be where I'm going to run into some issues. So this, if you look at this, this does not work with basic substitution. If you let u be this, the derivative of that's just 2. That's a z. That doesn't work. Also, notice I'm striking my z's. I recommend you strike your z's so you don't confuse them with 2's. Okay, so you look at that a little bit and then you go, oh, wait a minute, hold on, I've seen something like this before. Integration by parts. If I let u be the z, I know that in the new integral it's going to be a 1, or dz. And then dv would have to be the other part, which is e to the 2z dz. And I should be able to integrate this. So integrating from here to here, I'm not going to show that. Everyone should know how to do that at some point here, or by this time you should be able to integrate that. It's itself, but then you have to scale out the 2, so you put a 1/2 in front. And then over here you get du is dz. And then the ultraviolet minus voodoo, the voodoo part of it is nice, because when you put these two together, you don't have that z anymore. So this becomes ultraviolet, which is z times this, so 1/2 z e to the 2z minus integral this times this, so 1/2's coming out, e to the 2z dz. And then to integrate this, well, you already did that. From here to here was integration. So it's going to be this again with the 1/2 that's going to pop out. So we get 1/2 z e to the 2z, and then minus 1/4 e to the 2z. So that 1/2 that came out joined up with this one. These both have an e to the 2z in them, so I'm going to factor out an e to the 2z and be left with 1/2 z minus 1/4, like that. All right, I think that that's good. All right, so back here. This will be equal to the limit as t approaches negative infinity of this antiderivative, e to the 2z times 1/2 z minus 1/4, and then evaluated negative, or sorry, not negative infinity, that's my t, up to 0. And now I'll plug in the two values. Limit t goes to negative infinity of, and then I'll have two things here. So we plug in 0. E to the 0 is 1, and then 0, then minus 1/4. And then over here we plug in t, so we get e to the 2t times 1/2 t minus 1/4, like that. All right, now at this point I need to plug in negative infinity. So what's going to happen here? This is rather tricky problem at this point, because I need to figure out what happens to this. If I let t become negative infinity, 2 times negative infinity is still negative infinity. So that first piece right there looks like e to the negative infinity. Now we already know that that goes to 0. The problem is that we're multiplying that times this, and half of negative infinity is still negative infinity, and infinity take away 1/4, you're still negative infinity. So you've got something like 0 times negative infinity. And that is still an indeterminate form. We do not know what that turns into. We have to do more with this. So this is something that we ran into, hopefully you ran into in Calculus 1. So what I'm going to do is try and remember what this was. This was negative 1/4, this first one. And then I need to figure out this limit. I'm going to subtract it. So subtract whatever this limit is. The limit is t goes to negative infinity of e to the 2t times 1/2 t minus 1/4. All right, so let's see. Anytime we get that, 0 times infinity, whenever we ran into that in Cal 1, or if we had 0 times negative infinity, it didn't matter. What we need to do is pick one of them and drop it down and make a fraction, make a ratio out of it. So I'm going to rewrite this as limit t goes to negative infinity. I'm going to choose to drop this one down. So I'm going to leave 1/2 t minus 4 over, and then I'm going to write e to the negative 2t. And now let's just double check to see what happens. If t goes to negative infinity, then this becomes negative infinity minus a fourth. That top is still going to negative infinity. But now on the bottom, something different happens. Negative infinity here, if you take a negative 2 times another negative number, that's a positive number. So now the bottom's going to e to the positive infinity, which blows up. That becomes infinite. So this is over infinity. Anytime we have infinity over infinity, we can apply L'Hopital's rule. So that's the key to dropping that down, is that it'll create this form. So this, by L'Hopital's rule, and people do it different ways. I do an L, some people do an H, just to let everyone know they're about to use L'Hopital's rule. If you don't remember L'Hopital's rule, please look it up in the book. There's a whole section on it. I've got videos on it. Oh, I didn't do the rule. The rule says you just take derivative of the top and derivative of the bottom. So the derivative of the top is just 1/2. And the derivative of the bottom is the derivative of this. So derivative of e to anything is itself times the derivative of what's up here, negative 2. And then what you do is you reapply the limit. So as t goes to infinity, nothing happens up here. We just get 1/2 on top. But the bottom, again, the negative and the negative together become a positive, and this is e to the positive infinity. That's going to become huge times negative 2. It's still huge. This thing is becoming infinite. And, well, it's actually negative, but it doesn't matter. You have a fixed number over infinity. That thing goes to 0. So what I know is that this whole limit right here goes to 0, which means that my answer is negative 1/4. Interesting. Yep, all that for nothing. Well, we got negative 1/4 though. That was still good. You got more, or are you okay? Or?
I'm just going to practice now.
Okay. Okay.
Do you mind if I take a look out of your book?
Yeah, go ahead. Let me write the next problem down, and I'll work on that while you look at the book. Yeah, y'all don't have anything due this week, right? Yeah, take this time to catch up, or to get on, get everything in order. 17, integral 1 to infinity, natural log x, or x dx. If you have a piece of paper, do you mind sticking a piece of paper in here so I can flip back to it real quick? Okay, on this one, integrating from 1 out to infinity, the only discontinuity I have is actually at 1. That's the only, I'm sorry, not 1. At 0 is where we get undefined on the bottom. At 1, the top is 0, but the bottom is 1, so that's okay. So from 1 to the right, this thing is defined. We're in good shape. So I need to integrate that thing. And I realize I can make a basic substitution. The derivative of that is 1 over x dx, which I have here, right? If I rewrote this, that's the same problem. So this is just going to become integral u du. That's pretty simple. That doesn't get much easier than that. So 1/2 u squared is the antiderivative, which is going to be 1/2 natural log of x. That quantity squared. So be careful, we're not squaring the x, we're squaring the natural log. So this becomes the limit as t goes to infinity of the antiderivative, which is that, 1/2 natural log x squared, evaluated, let's see, 1 and t, which is the limit as t goes to infinity of, and then we have two things here. So first plug in t, 1/2 natural log t, that quantity squared, And then let's see, if we plug in 1, natural log of 1 is 0. So that's nice. And then let t go to infinity. If you let t go to infinity here, natural log of infinity gets big and blows up. Squaring it blows it up. 1/2 times that still blows up. This thing is infinite, so it diverges.
The assignment was 1 through 41, right?
I don't recall.
It was all of them.
Let's see. There it is, there it is. All right, so on this one, we do need to be a little careful because there is a possibility that the denominator could be 0. So let me talk about that. If I factor that, I get 2 solutions, 0 and -1. And fortunately for us, we're integrating from 1 to infinity this way, and both of the zeros that we have are here and here. So we don't have any discontinuities in the interval that we're integrating over. So I'm free to integrate. But to integrate that, I'm going to have to use partial fraction decomposition. So I'm going to rewrite the integral. I'm going to factor out the denominator. And then I'm going to go ahead and do my work now. I need to rewrite this as a over x plus b over x plus 1. And then 1 equals a times x plus 1 plus bx. And then this is one of those ones you can do the short method on. If I let x be equal to 0, I get 1 equals a. That killed off this one. If I let x be equal to -1, then you're going to get 1 equals negative b, so b is -1. So this integral turns into a over x, which is 1 over x, plus b over -1 over x plus 1 dx. And the antiderivative here is pretty clean. It's natural log, absolute value of x. I'll bring the -1 out front. -1, natural log x plus 1. All right, good to go there now. So we come back over here. We set up our limit as t goes to infinity of this antiderivative, which is that thing, 1 over x minus, the antiderivative, natural log of x minus the natural log of x plus 1, evaluated 1 to t. Ooh, this could be a little tricky here. I can already see what's going to happen. Just thinking ahead here. When t goes to infinity and I plug that in, I'm going to get natural log of infinity minus natural log of infinity. So you get like infinity minus infinity, which is not a good situation. So before I proceed, I'm just going to use a property of logs here. And if we have subtraction between two logs, we can turn it into a single log and turn it into division. So x over x plus 1 instead. And what's good about that is when I do plug in the t and I get infinity over infinity, I can use L'Hopital's rule. But I'll deal with that in a second. So that's where we're at. And now this turns into two pieces. So limit t goes to infinity of, got two things being subtracted here. So first let's plug in t. You get natural log t over t plus 1. Then we plug in 1, you get natural log of 1 over 1 plus 1 is 2, so 1/2. All right, when we let this limit t go to infinity, we get infinity over infinity. We need to figure out what that is. So real quick, limit t goes to infinity, t over t plus 1 equals, by L'Hopital's rule, limit t goes to infinity. Derivative of the top is 1, derivative of the bottom is 1, so the answer is just 1. So this is going to 1 in here, and then natural log of 1 is 0. So you get 0 here, and then you get minus natural log of 1/2. And that would be the answer. Although you can move the negative up as a power, like a -1 on that. And when you have a negative power, -1 power on a fraction, it flips it. So you can get natural log 2 as your answer. What number was that? Okay, so we're on 21 now. Ooh, 21 looks fun. How you doing?
Did you ask them to use this one?
Yeah, I did. Why?
I don't know, because it was very funny when I was coming in here. They
Oh.
were pointing.
Yeah. Yeah, they don't, I don't know why. This room is totally underutilized. Like it doesn't get, it doesn't get used the way it's supposed to be used. But then when I ask to use it for something like this, they're like, well, I don't know. And it's like, nobody's in here. That other conference room, they're having we have a committee that's visiting the campus today. And it's for our accreditation. It's the Southern Association of Community Colleges, blah, blah, blah. And they basically, once every few years, come out and evaluate the college and then give us the approval stamp that we're an accredited college. And they're here this week. So that conference room that I usually use is all set up. That's why they were cleaning it up last week, because they're getting ready for this big visit. So,
So do they go to the professor?
no. In fact, the last, I don't think I've ever talked with them when they're here. But there's always the potential where they could. They could just walk in and be like, hey, and start asking you questions. And so, yeah. Where did my marker go? All right, you good? You have a question?
I'm just working from.
Okay. Let me know if you need anything. I'm getting kind of burnt out on these here. Negative infinity to infinity. X squared over 9 plus x to the 6th dx. How's it going? You found us.
Yeah.
I figured it might be hard to find this room. Make yourself at home anywhere. I'm working problems from the next homework assignment right now. He's doing partial fraction problems, and after I finish this problem, I'll help you out if you have any questions. Okay, I'm going to need to integrate that. There's no discontinuities here. The denominator can never be 0, so I don't have to worry about anything in terms of discontinuities. But since I'm going from negative infinity to infinity, I will need to split this into 2 integrals. But the overriding thing is I'm going to have to find the antiderivative of that. So let me do that right here. So I see something here that x to the 6th was kind of a problem, but it's actually going to be a good thing because x to the 6th is x cubed squared. And if I let u be equal to x cubed, the derivative, 3x squared dx, I almost have right here. So I'm off by a constant, and that's okay. And so I can rewrite this integral. The x squared dx is this, so I'm going to have a 1/3 du. Over here, this x squared dx is gone. I have a 1 over 9 plus, and then this x cubed was u, so u squared. And that, I hope that you would recognize, is going to require arctangent. That's just a formula. So this becomes 1/3 times, now for us, this is a squared, which means a is 3. So the formula for arctangent is 1 over a, arctangent of u over a, and that's going to be 1/9 arctangent of u over a, but u is x cubed, so x cubed over 3. That's the antiderivative. And then back over here. So this becomes, split it up first into 2 integrals. I'll go to 0. Then from 0, I'll go to infinity. And then each one of those turns into a limit. So we've got limit t goes to negative infinity of, let's see here, the antiderivative of this, which is 1/9 arctangent. I'll give myself a little more room. X cubed over 3 evaluated from t to 0. So I've got to figure out what that is. Then I've got to go plus limit, this time t is going to go to positive infinity, of the same antiderivative, 1/9 arctangent x cubed over 3, this time going from 0 to t. So I'm going to get two things out of this. I think that's enough room. Limit t goes to negative infinity of, let's see, this minus this. Then I'll have another one, but let me do this one first. If I plug 0 in, I get 0 here. Arctangent of 0 is 0. And then times 1/9, it doesn't matter. So, okay, that whole thing is 0 right here, this first one. Minus, now I plug in t, so I can't really do anything with that. So 1/9 arctangent of t cubed over 3. And then I'll do this limit. So limit t goes to positive infinity of, again, two things. I know when I plug in t, I just get that expression again. When I plug in 0, I did that over there, I'm going to get the 0 again. And now I'm going to take the limit. Is that my phone? Okay. Take the limit again. All right. If I plug in negative infinity in here, a negative number cubed is still negative. So I get negative infinity on top over 3, it's still negative infinity. So the question becomes, what is arctangent of negative infinity? Well, to understand what's happening here, you go back and you look at the tangent function. This is tangent of x. And tangent of x has vertical asymptotes of pi over 2 and negative pi over 2. So when you say, what's the inverse tangent of negative infinity, you're saying at what angle do you get negative infinity out of the tangent function? And we know we can never do it, but it's a limit. That's what is it approaching? So to get negative infinity, we come down like this. That happens when x is negative pi over 2. So this right here is going to turn into negative pi over 2. So I have equals, the 0's gone, negative 1/9 times, and I just said that this piece right here is negative pi over 2. So that takes care of that. Now over here, same thing, but this time going to positive infinity. Positive infinity cubed is still positive infinity. So this time you're asking, what is arctangent of positive infinity? And that's going to be this side right here. So you go to positive infinity, that happens at pi over 2. So this thing is pi over 2. So this will turn into plus 1/9 times this, which is pi over 2. And then you have 0, so it doesn't matter. And when you put these two together, these two negatives multiplied to be positive, you get pi over 18 plus pi over 18, which is 2 pi over 18, which is pi over 9. So the area is pi over 9. I don't remember that being the answer, but it is. Okay. Do you have any questions, Zach? No? Did you have a good weekend, Zach? Work a lot? Do you get all that car stuff taken care of? No? All right. You worked 57 hours? Oh my gosh. Are you good? Sure. Okay. All right. 23. So I only have 1, 2, 3, 4, 5 more to go. 23. Integral 0 to 1, 3 over x to the 5th dx. Bam. All right, so
So this is kind of simple, but the limit makes it thrown off.
yeah, having that additional piece there, the integrations usually aren't as bad in this section, but it can be anything. Like I've done the first few here, and I've done integration by parts, I've done partial fraction decomposition, I've done basic substitution. So the integrals can be kind of whatever. But it's that limit stuff. Like, I don't know if you just saw what I did with that arctangent.
I remember.
Yeah, so. All right, so this is the first one I've done so far that has that's the type 2, because these are not, neither one of these are going to infinity. And we do have a discontinuity. If x is 0, then this isn't defined, but 0 is part of my interval. So when we're looking at this, my interval goes from 0 to 1. I'm trying to find the area underneath the curve here, but at 0 I know I have some sort of asymptote, so my function probably does something like takes off to infinity. Let's see, at 1 it just comes over here. I think at 1 it's at 3. That's how high it is. So I'm trying to find the area under here, but we have this infinite zone, this infinite region up here. So what we do is because our interval is to the right of 0, then when we come in this way, we're going to have to set up our limit as follows. The limit as t approaches 0 from the right side, so a little plus symbol there, of the integral from t to 1 of 3 over x to the 5th dx. So replacing the 0 with t, and then at the end we'll let t go to 0 from the right. So antiderivative there. This one hopefully doesn't require much thought. There's our integral. We just use power rule on this, so add 1 to that, you get -4, so it's going to be -3/4 x to the -4, or -3 over 4x to the 4th. That's your antiderivative. So this becomes limit, let's see, limit t goes to 0 from the right of the antiderivative of that, which is -3 over 4x to the 4th, evaluated t to 1. And that equals limit t goes to 0 from the right of, and then we'll have our two pieces here. So let me plug 1 in first. So 1 into there would be -3 over 4, that's it. And when I plug in t, I get -3 over 4t to the 4th. So now if I let t go to 0, this right here is going to turn into a fixed number on top over something that is heading to 0. And anytime we have a fixed number on top over something that's heading to 0, this thing is going to be heading to infinity or negative infinity, or the limit could not even exist. It does not exist. So either way you look at it, if it turns out to be positive, negative infinity, or does not exist, we can conclude that this limit, or this integral, is going to diverge, because we need this to go to a number for us to have an answer. So the answer is diverges because of that. Let's see here. 25. Integral -2 to 14 of dx over the square root of, fourth root of x plus 2. Let me draw my interval here. -2 to 14 is where we're looking. But you can see here that if I plug in -2 here, I'm going to get 0, and that's undefined. So I know I have a discontinuity here. So again, it's doing something like becoming infinite here, and we have an area. Over here, it's going to be finite. Let's see if we can figure out what it is. 14 in here, 14 plus 2 is 16. And then you get the 4th root of 16, which is 2, so it's 1/2, something like that. So it's doing that. So we have area here, but then that one becomes an infinite region. So let's see if this converges or diverges. This is going to be approaching -2 from the right. So I'm going to have limit. T is approaching -2 from the right of the integral t to 14 dx over 4th root x plus 2. So I'm going to have to figure out what that antiderivative is, so I'll work on that over here. I need the antiderivative of 1 over 4th root x plus 2 dx. Basic u sub here. And I can rewrite this integral as 1 over the 4th root of u du, which is integral u to the -1/4 du, which turns into, adding 1 to that, you get 3/4, so flip over 4/3 u to the 3/4, which is 4/3 x plus 2 to the 3/4. So this becomes now this limit, and then the antiderivative of this evaluated at the two endpoints. So I'm going to just save myself a little time here. It's this, and then 4/3 x plus 2 to the 3/4 evaluated t to 14. This will equal the limit. T goes to -2 from the right of, and then now my two pieces. All right, so we plug in 14 first. So 14 into here, we get 16. 16 to the 3/4 is the same as the 4th root of 16 cubed. The 4th root of 16 is 2. 2 cubed is 8. So this is 8, right? When we plug in 14, we get 8 here. Then times 4. 8 times 4 is 32. 32 over 3. And then we plug in t. So replace t in here. We get 4/3 t plus 2 to the 3/4. And now what I need to do is let t approach -2. So if I let t become -2, this right here becomes -2. -2 plus 2 is 0, and 0 to any power should be 0. The only thing I have to pay attention to is that I'm approaching it from the right. And the reason that's important, I guess, is because if you come in from the right, you're looking at numbers like -1.99999, that when I put something like that in here, I'm going to get a very, very small positive number. And that's good because I'm going to be taking the 4th root of it. So if I'm taking the 4th root of a very small positive number, then that's possible. If I was coming in the other way, then this would be like -2.0001, let's say. Then when I plug that in here, I'm going to get a little negative number in here, and I cannot take the 4th root of a negative number, so I wouldn't be able to do this. So that's why the one-sided limit is important. But because I don't have to worry about it, this is going to be 0, kills everything off. So the only thing left is 32 over 3. Oh, the answer is 32 over 3. All right, so this problem is a little different than the ones that I've done before, because if I plug in 9, there's no problems here. If I plug in 0, hold on, that can't be all right. Is that right? X minus 1. Oh yeah, okay. If I plug in 0, there's not a problem either, because I can take the cube root of a negative number. That's okay. The only issue I really have is if this denominator here is 0. So if x is 1, I have a problem, and 1 is in my interval. So looking at my interval, here's 0, here's 9. Right. The problem I have is right here at 1. I have this discontinuity. So the function's doing something where it's blowing up on one side, blowing up on the other, and I need to figure out if the area here in this region is going to be finite or not. So what I'll do is I'll have to first split this integral up into two pieces, 0 to 1, and then 1 to 9. And each of these is going to be a limit. So limit, 1 is where I have the issue. So I go limit t approaches 1. And since this integral represents this first side over here, I'm approaching 1 from the left side. So 1 from the left of the integral 0 to t 1 over cube root of x minus 1 dx. Then plus another limit. T is approaching 1 this time, so I'm working on this one. 1 is where the problem is. This time I'm on this side, so I'm approaching 1 from the right of the integral from t to 9, 1 over cube root of x minus 1 dx. Now I need to figure out what that antiderivative is. Integral 1 over cube root of x minus 1. This is a basic u sub. U is x minus 1, du is dx. This becomes integral u to the negative 1/3 du, which is going to be 3/2 u to the 2/3, which is 3/2 x minus 1 to the 2/3. All right, so now I'm going to rewrite these limits. Or, yeah, these integrals which involve limits. So this first one becomes limit t approaches 1 from the left of the antiderivative of this, which is 3/2 x minus 1 to the 2/3. Evaluated from 0 to t, plus limit t goes to 1 from the right of 3/2 x minus 1 to the 2/3, evaluated this time from t to 9. This is limit t approaches 1 from the right, from the left, I'm sorry, of two things here. Let's see if I can squeeze these in right here. I'm going to plug t in first, which doesn't change anything. T, sorry. Then I'm going to plug in 0. So that was the first piece, minus when I plug in 0. I get negative 1 here. Negative 1 to the 2/3 is the same as the cube root of negative 1 squared. Cube root of negative 1 is negative 1, but then squared I get 1. So that's going to give me a 1 there. And then, sorry, then I had a 3/2 in front. So 3/2. I need to figure out what that is. Then this one, limit t approaches 1 from the right of, again, now I'm going to plug in two things. So let's try 9. 9 in here. 9 minus 1 is 8. 8 to the 2/3. 8 to the 2/3 is the cube root of 8 squared, which is 2 squared, which is 4. And then I multiply times 3 halves. So 3 halves times 4, let's get 6. So when I plug in 9, I get 6. And then minus, now I plug in t. When I plug in t, I get 3 halves, t minus 1 to the 2/3. All right. But t go to 1. If t goes to 1, this is 0, that whole thing's gone. Over here, if t goes to 1, this is 0, the whole thing's gone. So I'm getting negative 3 halves here. Over here is 6 plus 6, which is going to be, see if I can do my simple math here, negative 3 halves plus 12 halves, which is 9 halves. I feel like I got that answer earlier for a different problem. I guess not. All right, 27's done. Hey, Zach, didn't you say you wanted to do problems today? Like you just wanted to get up and do problems?
I'm trying to get back into thinking mode. So
Okay.
I'm going over the videos for the homework for 6.3.
Okay. So, wait a minute. I only have 2 left. 29 and 31. All right, so the only issue I'd run into here, division by 0, would occur if e to the x minus 1 was 0. But that happens when e to the x is equal to 1. And you can tell here if I raise e to the 0, I get 1. So if x is 0, I have a problem. And 0 is within my interval. 0 is in here. So I'm going to have something happening there. It's not good. So I'm going to have to approach it from both sides. So I have to break this up into 2 integrals. So it'll be integral from negative 1 to 0 first. And then the integral from 0 to 1. And then I'll have to put the limits in there. But before I do that, let me integrate this. Basic u sub. And then that becomes integral 1 over u du, which is natural log of u, which is natural log of e to the x. But that's just x. So that's kind of weird that we just get x. So you might be saying to yourself, well, how in the world, oh wait, sorry, e to the x minus 1, that didn't seem right. Okay, e to the x minus 1. U is e to the x minus 1, not e to the x. So I can't simplify this at all. All right, so we got limit t goes to 0, and I'm on this integral, so I'm over here. I'm going to be approaching 0 from the left of the antiderivative of this, which is natural log, absolute value of e to the x minus 1, evaluated from negative 1 to t. And then I set up this integral, plus limit, this time t is approaching 0 from the right side, because I'm on this one, of the antiderivative of that, which is natural log of e to the x minus 1, evaluated from 0 to 1, but 0 is the t. Now I'm just going to write out break it up into the 2 pieces, each one of those. So this first one is limit t approaches 0 from the left of, okay, plug t in first. Natural log, absolute value, e to the t minus 1. And then minus, now plug in negative 1. So e to the negative 1 minus 1. So natural log of e to the negative 1 minus 1. That's just some number. I don't know what it is. And then we set up the next one, which will be plus limit as t approaches 0 from the right of, again, two things. First we plug in 1, natural log e to the 1 minus 1, and then we get minus, plug in t, natural log e to the t minus 1, and then close it off. All right, let's let t go to 0. T goes to 0 here, e to the 0 is going to be 1, 1 minus 1 is 0, natural log of 0 is undefined, but really we're saying what's the behavior of natural log as you approach 0. So if you're on the natural log function, as you head towards 0, the natural log function dips down to negative infinity. So this whole expression is going to negative infinity. And at that point we can stop because that means the entire integral diverges. So you could check, this is just a number, this one's a number, but then again, this one goes to negative infinity, so you have a problem, so diverges. Last one, I think. Integral 0 to 2, oh no. Integral 0 to 2 z squared natural log z dz. I'm going to take care of the integral first, the integration. So integral z squared natural log z dz. I'm going to use integration by parts. U is going to be the natural log of z. dv is going to be z squared dz. The antiderivative here is 1/3 z cubed. The derivative here is 1 over z dz. And so this integral becomes ultraviolet, this times this, 1/3 z cubed times natural log z minus this times this, the 1/3 comes out, integral z cubed, and then 1 over z multiplied to give you just z squared dz. And then I can integrate that. That's going to give me another 1/3 z cubed times that. So 1/3 z squared natural log z minus 1/9 z cubed. So now let's talk about where this is having some issues. The only problem I have, I can plug in any number here and square it, that's not a problem, but the natural log function is not defined at 0, and 0 is part of my interval. So my interval is 0 to 2. I have to approach 0 from the left-hand, or from the right-hand side. So I'm going to do a limit. T is going to approach 0 from the right-hand side of the antiderivative of this, evaluated here and here. So antiderivative is 1/3 z squared natural log z minus 1/9 z cubed, evaluated. The bottom one was 0, but that's my t, up to 2. So this is equal to natural, or limit, sorry, t goes to 0 from the right, and now I have two pieces. First we'll plug in 2. So 2 squared is 4, so 4/3 natural log 2 minus, see, 2 cubed is 8, so 8/9. And that's just a number, something. Minus, now we plug t into this, and we get 1/3 t squared natural log t minus 1/9 t cubed. All right, now if I let t go to 0, that's 0, and this is natural log of 0, and then that's 0, but that's 0, so I don't need to worry about that. But this one right here, I need to investigate, because I get a 0 times, and we just said a second ago that as natural log heads towards 0, it goes to negative infinity. So we have that special case. So let's take a look at how we can deal with that. Limit t goes to 0 from the right of t squared times natural log t. I'm going to rewrite that as natural log t over t to the negative 2. So I drop the t squared down. And remember that that's really the same as natural log t over 1 over t squared. And now, as t goes to 0, we said the top goes to negative infinity. And the bottom, as t goes to 0, you get a fixed number over 0. That goes to infinity also. So you get infinity over infinity. So I can use L'Hopital's rule on this. Derivative of the top is 1 over t. Derivative of the bottom is negative 2t to the negative 3. So this is the same as limit t goes to 0 from the right, 1 over t over negative 2 over t cubed. And then when you flip that up, flip it, and then you can reduce the power. You get limit t goes to 0 from the right. What do we have here? T squared on top over negative 2 on the bottom. Now if t goes to 0, this just goes to 0. So that whole thing goes to 0. So if this whole thing goes to 0 times 1/3, that goes to 0. We already said that went to 0. And then over here, this would be our answer. So let me check that. That doesn't look familiar. Eight thirds natural log 2 minus 8/9. 8/3 natural log 2. Off on something here. Oh, ultraviolet. Oops. My bad. Oh, that changes everything. Shit. I'll try and fix it. I don't want to fix the video. This should have been a cubed. It was right in my integration by parts table. This was right. Ultraviolet should have been a cubed here. That would have made, when we plugged in 2, this would have been 8/3. So 2 goes into here. We get 8/3, and then same. This is still okay. But then over here, this should have been a 3. Still goes to 0 in negative infinity. Over here, this would have been a negative 3. This would have been a 3. Same thing happens. This derivative would have been a little different. 3 here, negative 4 here. And then this would have changed. Nothing's going to change in the answer. It's just that that little piece was off. So this is going to be negative 3 over t to the 4th. Flip it, t to the 4th over negative 3. So this is limit t goes to 0 from the right of t cubed over negative 3. And as t goes to 0, that goes to 0. The whole thing goes to 0. And so this whole thing still goes to 0. So we get the same exact result, except that this should have been 8/3 instead of the 4/3. So that's it for that.